So, welcome everyone to this presentation from the Coastal Highway Route E39. Today, Helgedagsrud is presenting wind loads on bridge decks using CFD and FSI methods. The recording will be put online afterwards, and those of you who are participating in the recording will not be shown in the recording unless you ask questions at the end, which is a possibility. Okay, the word is yours.
Okay, thank you, Kjersti. So today we're gonna look at FSI methods for wind modeling. Just to start, I'm a PhD candidate at Structural Engineering Department at NTNU. My main supervisor is Kjell Magne Mathisen. And my co-supervisor are Ola Iseth. I guess many of us know him in this around in this community, and Yuri Basilevs from Brown University. And he's a world-leading expert on computational sciences. So we're kind of blending some interesting expertises and in this project, and I think that is what we're trying to utilize. So we've been doing this for 2.5 years now, finishing before summer, so it's time to wrap up soon. So I'll try to give you sort of an overview. But before I start, I wish to thank Vegvesenet for this very interesting project. It's really stimulating to work amongst so many clever minds and to feel that your little contribution sort of adds to a bigger whole. So that is important for motivation and progress to me, I think. I also wish to acknowledge Dr. Tekin Olav Olsen, from where I am on an educational leave. So I appreciate their interest and support in this project. So today I'll start with some motivation. And I'll try to identify why we would need such advanced FSI modeling in these very practical tasks. And I'll spend quite some time on the computational method and try to give you an overview on how FSI is done in practice and some opportunities and limitations. And then we will see some applications and studies we have been doing, and also explore some further possibilities. So I think we'll, it's around 50 minutes, so that will leave us some time in the end for discussion. So yeah. But first of all, I'll show you this picture. So I don't think we need to spend any time on this. But as I see it, the challenge is kind of twofold, where we have, first of all, the technological challenges with the very wide fjords. But it's also, it cannot be done at any price, so we need to make it sufficiently low cost to really make it happen. So I feel that's the main challenge here. So we are concerning the wind loads and mainly dynamic ones. So I'm mostly concerned with this long span bridges, for example the TLPs, but mainly the suspension bridges, single span, and yeah, these are considered for span width up to 3,000 meters. So, and I think this graph here kind of presents the scope of the challenge and ambition, because here we have the historical view of the main span width length, and we aim up here. So that's kind of a giant leap, I would say, for engineering. And one of the problems with increasing the main span width is that the frequency ratio between torsion and heaving tends to drop. And that also seems to be the main driver for reducing the flutter stability limit. Traditionally, the quick fix for this problem has been to increase the torsional stiffness, of course, and that is equivalent with increasing the girder mass. And that grows at the volumetric rate, of course, and the strength of the bridge grows with a quadratic rate with the area of the cross of the cables. So it's obvious that this method has a limit, and I think that is kind of where we are now. So we must use some new ideas, and I think there are already some new directions in the state of the art. It's for example, been explored by Mikael Andersen. You can see his talk earlier. But if you really do sort of engineer the aerodynamics of the bridge deck, we can live with a low frequency ratio, but still have a stable bridge. So I think that is the way to go for the new super long span bridges. It has already been used for a couple of existing ones, this Chinese one and the Turkish under construction. But yeah, so we are facing some bridges with a extensive optimization of the aerodynamics. That's what I'm trying to say. So the way this is taken into design is typically an iterative process between a global analysis, where you sort of get the still air, the structural properties of the bridge, and you do a series of wind tunnel tests of the bridge deck segment. And you put this into the modal analysis, and you compare it to the design winds or wind measurements. And in this pipeline, we are studying if we can use CFD, FSI as a complement to this wind tunnel task. And yeah, we can, for example, partially replace some of the tests or supplement them. We can do some feed studies before we actually craft the model and go to the laboratory. We can do some validations. It's especially relevant for the bridges with curved surfaces, because they tend to be Reynolds number dependent, and that is something we where the wind tunnel tests fails. And yeah, perhaps study the flow patterns, and in the end of the day get a better understanding of the wind structure interactions and give the engineer a better night's sleep. So let's go to the computational method. I'll present an FSI framework, which is a coupling of different physics. And in our context, it's a coupling between the fluid mechanics and the structural mechanics, and some problem to conform the fluid mechanics to the motions of the structures. And these have some coupling between them. But let's start with the sub-problems. So if we start with the fluid mechanics is governed by the Navier-Stokes equations. And for low Mach numbers, we can use the incompressibility constraints. And with this, the equations is like this. We have the balance of linear momentum, the Kraftlikevekt, and so we have the accelerations, the mass accelerations here. We have the advection of the fluid, and the body forces should be balanced by divergence of stresses. There's one for each direction. And we have the mass balance. So what flows in needs to flow out. So this is the Navier-Stokes equations. Stresses is given by some isotropic pressure and the viscous stresses, which is driven by the strain rate of the fluid velocity, or the shear in the fluid. So this is the conservative form, which means that we have separation of the derivatives, which is very useful for numerical implementation. It's kind of a different story for compressible flows, but let's stick to the incompressible ones. The last thing we need to complete the statement of the fluid is the boundary conditions. They can, so if you have a fluid mechanics domain omega and the boundary gamma, we can specify the velocity on parts of the boundaries, like for example the inflow, or we can have some Neumann type tractions can be specified. Specify the pressures, for example. So, yeah, but since we live in a deformable domain, we have some structure that moves inside our fluid. We need to recast the fluid mechanics in a moving frame. And one way to do this is to make use of a reference domain omega hat to define at t0. And we have a current domain omega t, which is obtained by adding some time-dependent displacements to our original coordinates. So we have this mapping to the current domain. And from this mapping, we can also get the velocity of the fluid mechanics mesh, so to say. And yeah, with the moving domain extension, the Navier-Stokes takes this form. It's actually very little differences. The only difference is that we evaluate the accelerations in the current domain, and we have the domain velocity appearing in the advection term. So it's very little difference. It's easily implemented to existing codes. But in the end of the day, we have equipped the Navier-Stokes with a variable for the motions of the fluid mesh. This is the strong form, which means that it is satisfied in every point in space. For finite element implementation, we would need to find a weak form of the fluid mechanics equations. And I will not go very into detail here. This is just standard Galerkin method. But the problem, this is the Navier-Stokes will take this form now in the weak form, which means that it has changed to error minimalization problem. So it can be sort of you satisfy the Navier-Stokes equations inside an element rather than in every point in space. So this is the point of departure for numerical implementation and discretization. We collect these terms into an operator that kind of solves the Navier-Stokes. And this works perfectly fine until you realize that you have turbulence. Because turbulence is an energy dissipating process where the kinetic energy of the turbulence is transferred into heat. And this heat, this dissipation follows the so-called Kolmogorov energy cascade, where large turbulent structures is sort of transfers into smaller and smaller structures until you hit the viscous subrange, where the rest of the energy is killed. So this is the logarithm of the energy. You have the wave numbers here. So the majority of the energy is for the large structures. But I think it's time to recall the Reynolds number, because it's the ratio between inertial and viscous forces, which can be stated as some characteristic length scale times the velocity divided by the viscosity of the fluid. And where the dissipation is driven by, as I said, the viscous stresses. So where those start to dominate, it is at the Reynolds number 1, which for our applications are for like 10 to the minus 6th meter. And for our applications, that would, to resolve this, we would need like 10 to the power of 18 grid points. So I think, which can obviously not be affordable. So that is why we need a turbulence model. There are some families of turbulence models. The most crude one is the Reynolds average Navier-Stokes. which sort of solves the average quantities. So it works for, it's very powerful for stationary simulations, but it fails for unsteady aerodynamics. So the next one is the large energy simulation. Here you actually simulate the turbulent structures, but you make sure to dissipate the energy before the fluctuations vanishes out of your resoluted scales. You also have the direct numerical simulation that actually resolves everything, and it's not relevant for industrial applications, but you have a series of benchmark problems where you have DNS results. We use the so-called residual-based variational multiscale formulation, which is in the family of LES-type models, in the sense that it decomposes the turbulence into scales that you have resolved and the ones you have not. I will not go very deeply into this, but it differs from other LES methods like the Smagorinsky type in the way we decompose the turbulence. But because instead of using the so-called this filter functions, we sort of use the residual of the analytical solution to add viscosity to the high wave numbers. So it has the advantage of having no ad hoc devices like the eddy viscosity, and it also works perfectly for all flow regimes, like the boundary layers or for laminar flows, or you can even converge to DNS if in mesh refinement. And it's also numerical consistent, so it offers full convergence. There's a bunch of terms, but we collect them in this VMS operator and add them to the fluid mechanics. Next, I'd like to revisit the boundary conditions, because the physical boundary condition at solid surfaces is the zero velocity. And for our bridge applications, we have very high Reynolds numbers and thus very thin boundary layers, which is a sticky layer at the solid surfaces, which is in order of 10th of a millimeter. But one way we can resolve or relax the need for resoluting these boundary layers is to use the so-called weakly enforced boundary conditions. And just to show you an example, this is from our first paper, and compares strong and weak boundary conditions for a very crude mesh. And we can see that with the strong, we have this very, it seems like the bridge is flowing in syrup. We have thick boundary layers, and it's obviously non-physical. But with the weak, we have sort of enforced the no-slip with a penalty-like formulation, and the flow is allowed to slip. We get a much more correct pressure distribution and forces. So this is a very powerful tool for efficient computations. We collect the terms in the weak boundary condition operator and add them to the fluid mechanics. So this completes the fluid mechanics, and we move to the structural mechanics now. You can basically use any formulation here, solids or shells. Shells are commonly used. But I'll go for a simple one, because if we consider our bridge deck segments as rigid, which is a good approximation, I would say, for our applications, we can describe the dynamics of the bridge with the motions and rotations of the center of gravity. And the structural mechanics problem is the balance of this body is then given by the balance of linear and angular momentum of the center of gravity alone. Kraft, moment, like vekt. So we have, in essence, we have the inertial forces should be balanced by the forces that is given by the gravity and the tractions. And these are the tractions from the fluid mechanics. And for the rotational part, we have the rotation inertia, which is balanced by the leverage of the tractions. And the gravity is cancelled out. And we have also augmented the formulation with external damping and stiffness, with the free vibration in mind. So yeah, this is given in detail in our third paper. So this is now reduced to 6 equations in 3D. Even easier if you have forced vibrations. You have just a closed form expression for the displacement and rotations, and you don't need to solve the equations at all. So yeah, with the displacements of the body, we can move to the last sub-problem, which is the fluid mesh problem, and we can now recall that we have a variable for the fluid mechanics position in our Navier-Stokes equations. And we can use this variable to solve the elastic equation for the fluid mechanics interior, where we use the structural motions as the displacement type boundary conditions. And for the material, we use a very non-physical one. We scale the Young's modulus with the inverse of the Jacobian, such that small elements become stiff and large elements become soft. So you can see that we get a very nice deformation pattern where we have avoid wrapping and distortion for very large rotations and displacements. So with the sub-problems at hand, we can go to the coupled problem. We now have our sub-problems collected in these operators. And all of these are in general dependent on the fluid velocities and pressure, structural motions, and the motions of the fluid mechanics interior. And as it turns out, most of these terms are exactly 0 or approximately 0. So we can take them out and we get this nice diagonal structure. It's uncoupled and we can use a staggered solver. So in the end of the day, what we do is that we solve the fluid mechanics and we give the tractions to the structural mechanics and we find the equilibrium position of the structure, and we pass the displacement to the fluid mesh problem, and we then deform the fluid mechanics domain to conform the structure. We can do a couple of iterations and we then advance to the next time step. So that is the FSI. For the simulations, we typically test bridge deck segments 1 to 2 times wider than the width of the deck. So it may look like this. This is some of our first meshes. It's the finite elements, linear tets, and both are for the Hardanger. Here's the. We also do isogeometric analysis, which is a very promising analysis framework. We then use structured meshes for having higher order continuity. Here's another picture. It's the Hardanger bridge with the spoilers installed. And yeah, we typically have like 1 million nodes. We can have a few less with the IGA. But anyway, efficient computation requires some parallelization. So we typically decompose the problem to 500 sub-problems and distribute them to CPUs on the supercomputers. So mapping may look like this. Yeah. So this is the typical mesh. So before we go to the applications, I think I would just take the aerodynamic forces as our point of departure. Because, yeah, let us consider this slender bridge. And if we consider assume that we can use a strict assumption. We can express the forces as drag, lift, and pitching moment at a given position and time. If we do the modal decomposition, we can express the dynamic equilibrium like this. We have the modal quantities of the structure on the left, and we have the forces on the right in terms of the generalized coordinates eta. The forces are typically decomposed into a mean part or a dead load that can be taken out of this dynamic equation. Some self-excited forces that arise from the motions of the bridge deck, and we have the buffeting forces from the turbulence in the wind. And these are the dominating one for the strong wind load cases. There are also other loads, but let's focus on these. So if you start with the self-excited forces, I think this has been covered very well in earlier presentations, so I'll not go too deeply. But the self-excited forces are typically given as portions of the structural positions and velocities, and these aerodynamic derivatives, which are the transfer functions to the forces. And on this form, we see that we can consider the self-excited forces as modifications of the damping and stiffness of the structure. And we can take them to the left-hand side of the equations of motion. And we are given an aeroelastic system whose behavior is depending on the wind velocity and vibration frequency of the structure. So if we consider this aeroelastic system, we can solve the eigenvalue problem to give us the flutter characteristics. I forgot to say that self-excited forces is the mechanism that drives the flutter. And for oscillating systems, the eigenvalues appear as complex conjugates, where you have the imaginary part as the oscillation frequency, and you have the real part as the decay, which is hopefully negative, so you have a decaying response. But if your real part switches sign at some wind velocity, you have a divergent system, which is recognized as flutter. And this is the point where I bring up this guy. It's a torsional divergence, but it's sort of the same thing, and it marked the starting point for flutter analysis. And we have to prove that the critical velocity of the flutter velocity satisfy the design velocity. So this is from N400. So we need to find the flutter derivatives or the aerodynamic derivatives. Perhaps the easiest way is by forced vibrations, where we move the bridge deck in a prescribed motion, and we measure the corresponding forces. So here's the simulation, and we have the dashed line, that's the wind tunnel. So it's a pretty good match. We have to test a handful of modes and wind velocities to find the frequency dependence. So we have here's another one, this is for the pitching, and we can see it corresponds well with the wind tunnel as well. And in the end of the day, we can get the flutter derivatives. So this is the numerical simulation, the blue circles, and we have the wind tunnel experiments. And in general, they match pretty well. This represents a phase shift of the load. It's pretty ill conditioned, so it kind of skyrockets. But to find out what this really means for in practice is if we take these aerodynamic derivatives, we put them into the equations of motion, and we solve the eigenvalue problem. For reference, we tested flutter experimentally with a free vibration in the wind tunnel. So you can see the flutter mode here. This is the Hardanger bridge still. We have the critical velocity and frequency. And for the wind tunnel forced vibrations, and we got these predictions. So this is a solution of the eigenvalue problem, basically. And it's not exact science, but it matches pretty good. And here's the numerical simulations. And we get very good predictions, equally good actually as the companion forced vibration wind tunnel experiments. So we were very happy with these results. We can also study flutter with free vibrations. And then we don't use any assumptions of the loads or any equations at all. We just simulate this experiment directly. So it's nice verification. The first thing we did was to check if our formulation kind of worked. So we took the still wind vibrations. We can see we have the red line, that's the wind tunnel, and we have the simulation, and they pretty much coincide. And it's a very slow decay. It just keeps on forever. And if you add a bit of wind, 50% flutter, we see that the aerodynamic damping really kicks in, and we get the bridge comet at rest after just a few cycles. And we also capture this behavior very well. And then finally, we have flutter. So here's the same as the last slide, and this is the numerical simulations. So we can see that the video is kind of lagging, but we get really good predictions in both terms of the flutter mode and the critical velocity and frequency. So I think we really are really able to capture the flutter behavior with numerical simulation. So with that, we go on to buffeting. So buffeting is the turbulence-induced part of the dynamic loads. It's important in many limit states. I think we'll go quickly through this as well, but most often you decompose the wind into a mean part and some zero mean fluctuations, which are typically given in a statistical sense. And you also have the dynamic parts of the loads, which is the buffeting loads. So it's typically, it's given. We are given the statistics of this one, so we typically study in the frequency domain. So the power spectrum of the forces are typically given as the spectrum of the fluctuations and some transfer functions that are the aerodynamic admittance functions. So these are the ones we are interested to find, because these are given by design codes or measurements, and this goes into our dynamic analysis. But we need some way to simulate the incoming turbulence. So we propose this multi-domain modeling approach where we generate turbulence in a pre-computing domain here, and we project the outflow as inflow boundary conditions to the main computing domain. So in the pre-computing domain, we use a pressure-driven channel, a wall-bounded channel with periodic boundary conditions. So what flows out here comes in again here. And we see the turbulence sort of develops nicely. If you place a probe in the center of the channel, this laser, we can measure the velocity fluctuations, and they look nice and uncorrelated, suggesting an isotropic turbulence. The velocity spectrum looks like this, with the von Karman fitting here, and they conforms very well to the Kolmogorov energy cascade. And here we can also clearly see how the turbulence model works. It simulates the turbulence along here until we come to the unresolved scales, where the energy is rapidly dissipated. So this is sort of the highest wave number we have resolved in this simulation, and marks the upper limit. but we are mostly interested in low frequencies, so that's okay. For the bridge, we get inflowing turbulence. We'll ask the contours here, shows that. And we measure the forces, for example, in time domain, for the lift, or in the frequency domain. And we can see this green line is the uniform inflow. And we can see that we have clearly some low frequency content here. This is the buffeting. The signature turbulence looks like, yeah, it's similar, but we see this spike here. That's the vortex shedding, and we can see that the turbulence effectively kills the vortex shedding. So that was an interesting finding. But we now have the spectra at hand, and we can easily compute the aerodynamic admittance. We don't have any experimental results for this. It's actually a very difficult experiment to do, but we have the analytical solution for the airfoil, which we have also simulated. So it looks nice. And we can see the Hardanger and the rectangular section follows sort of the same pattern. It tends to drop a bit earlier. And we have the signature turbulence, which push it back up again. But this is not really a part of the buffeting. So it's another phenomena. So I would say the airfoil solution is a very good approximation for bluff bodies as well. At least for the lifting force. It should be mentioned that in the design codes, this is set to unity. And that is, in my opinion, a very radical, gives excessive buffeting forces for high frequencies at least. But yeah, in the end of the day, we were satisfied with the results, and we have submitted the results now very recently. There's also a lot of other things we can do with this framework, so it's kind of ongoing studies. We can study the span-wise coherence and lots of other things. But in the end, I want to address vortex-induced vibrations. And that is a vibration that is sort of the resonance if the vortex shedding frequency hits the eigenfrequencies of the structure. Of course, this is a serviceability concern, and we want to find out how big the oscillations are. So we studied the Hardanger bridge. This is I got these results last week. But we can see this is the Hardanger bridge with the spoilers installed, and this is without. It's a red line, so we can see that we get almost no excitation with the spoilers, thanks to the small vortex shedding forces of the attached flows. Whereas for the ones without, we can see the oscillations is larger because of it's also locks into a higher shedding of the forces. So yeah, these are just another application. The experiments will be conducted in the wind tunnel in January, but it looks very similar to me of the Svein Ole Hansen's experiments with the original Hardanger deck. So, but yeah, so I think we conclude our applications there, but in the end, I want to address some further challenges. And earlier this week, I got this image from Shu. He had this. This is the Bjørnafjorden floating bridge. It's a very wide deck with a low elevation, and he was asking, might CFD be something to look into for if you have a storm and you have this extreme wave coming? And this is sort of, you cannot do this with potential theory, and it's also a very difficult thing to do in the wind tunnel. So it might be something to look into for the simulations. So I can think of two approaches to this guy. We have a very analytical one, where you actually simulate the water itself. So you have a two-fluid FSI simulation. And for this, you can use the level set method. And just to quickly give an idea of the level set, we decompose the fluid mechanics domain into a water and air part. They are governed by the same equations. And we add a scalar function or a scalar field to our fluid mechanics, which is such that if it's negative, we can call it air, and if it's positive, we can call it water. And at the value of 0, we have the air-water interface. And we then use the Heaviside function to assign the material parameters. So say if you're negative, you get the density and viscosity of air, and if you're positive, you receive the water parameters. But how to determine this function phi? Well, if we assume that the air-water interface moves with the fluid particles, it can be given mathematically as the convective derivative. So this is the governing equation for the level set. And then for the early applications, they did this for the tank sloshing, and they experienced that you slowly lose water because of the leakage to air. So they added this mass balance term, added a constraint that says that you will have a constant mass. So this is a small extra constraint. But the good news is that these two new problems is just another works perfectly fine with our existing FSI framework. So we just add a few blocks to the already FSI existing FSI. So after the fluid mesh problem, we then solve the level set and determine phi, and we do the correction block here. So this works just perfectly fine in our existing framework, and we simulate the two fluids in an FSI setting. So I just put up this very quick example. This was rendered yesterday. It's just a very crude thing, but initialize this interface here and sort of excited the surface on this end. I'm sorry. So it kind of, yeah, you can see that you can simulate the waves traveling, and you actually simulate the interaction here. So you get you simulate the breaking of the waves. You have the topology changes and everything. Yeah, but this was just some put together very quickly yesterday. So it shows demonstrates the framework, and I would recommend that you elevate the bridge a few meters at least away from the surface. But yeah, but there's another very much simpler approach, because I guess for most extreme waves you know the profile, and you can then just use the existing technology of the functionality of the forced motion type boundary conditions to simulate the wave. So we can, for example, do the area wave and also get the tangential velocities here, but I just made this very quick example also yesterday, and this is like 11 lines of code. I counted it, and you can have this traveling, this wavelet traveling through your domain. And you then have a perfectly deterministic wave, and you can study the different winds and waves and so on. You have full control. So I think this example demonstrates the efficiency and flexibility of this FSI framework. So with this, I think we go to the conclusions. Just to recall, I think the further increase in the span width of the suspension bridges now happens on the premise of aerodynamic stability. And with the increasing number of wind tunnel testing, we were studying if we can use CFD FSI to complement and enhance this study. And just in an attempt to prove the accuracy, we have studied different applications on a few thoroughly studied sections, like the Hardanger and the rectangular section mainly. And yeah, we did flutter analysis with forced and free vibrations, and buffeting analysis with a new multi-domain modeling approach, and finally vortex-induced vibrations. And we get pretty good results, I would say, when we compare to the companion experiments. So in that sense, I would say that this work adds some confidence to the use of this FSI methods in practical bridge engineering. And I think that with the increasing computational power, it will have an increasingly important role in the future as well. But I have to say, though, that it's sort of a last reminder. CFD, as all other types of numerical methods, should be used with some caution, because if you don't really tune your meshes or parameters correctly, you can really get any results. So I think you really have to do this closely with the experiment and know how to get the correct results. So this is just a disclaimer, and with that I close my talk, and I thank you for staying with me. So yeah, I think we're at time as well.
Okay, thank you, Tore. And now it's open for questions. Maybe I would like to challenge Shu, if you are with us.
Yes. Yeah, I was waiting for someone first, and because I do have some comments or questions. First, thanks, Tura. You have given a very good presentation, and especially I was a bit surprised of your response time. Also, considering you are using CFD, right, for the problem I sent you, I think during this week. I think it's a quite nice demonstration, and how you, I think you have thought really given a good idea of how to simulate that. Except for that, and I think actually we have done a model test of this problem. I think in the last year we have used kind of 20 like plate to simulate the free surface, and carried out the model test of the bridge, floating bridge section, like what you have shown in the figure. So if you want to kind of tune a bit of your simulation, you can take contact with us. We have kind of that information data available. Yeah. And the second is about for this problem. Actually, we are also now in active communication with the consultants that is developing our floating bridge concept. This problem, I think, can be considered as two folds. One is that this wave-free surface elevation can give an actual, how to say, component of turbulence in the vertical. As we have communicated earlier, this week it represents like 8% more for the design case we have now. That is first, and second, of course, it has an effect on the coefficients itself of the bridge girder. Yeah.
Yeah.
Yeah. So not really questions, but kind of more information. Later, if you are interested to continue with this, we have more information that we can communicate. And also, we have now Jingao Wang. He's with us now in the project group as the aerodynamics part representative. Yeah. Yes.
Well, thanks for the comments. I think it's a very, very interesting study, and it's also an interesting task to do numerically. I would think so. I think we,
thanks.
And time we will go further on with this and see if we can capture this numerically.
Right.
Because, but if you apply, you can sort of apply if you apply the boundary conditions to the floor of your domain, that sort of corresponds to the tangential velocities and the velocities of the currents and so on. You can sort of, in that way, generate the turbulence over the wave. So it's you have the possibility to study that numerically. So.
Yeah, we have done 2 sets of tests. One is simulating this free surface as a plate without kind of vertical turbulence, and second with the free surface that is really kind of simulated free surface. Okay, thanks. Thanks again. I will give the time to the other audience that have questions.
Hi. Hello.
Go ahead with
May I
your
ask a question?
Yes.
Hi, Tura. Thank you very much for your presentation. I'm Shengnan from UIS. I'm also doing CFD simulations about oceans. So I'm really happy to see your presentation that you prove again that CFD can be used for the very critical real engineering problems. That's not everybody believe that. So I'm also very happy to see that. I have several small questions. The first one is I'm also doing the VIV simulations using dynamic mesh. So I saw you mentioned you use the mesh scheme proposed by Jacobin. So is it a special dynamic mesh, or is it the same with the traditional dynamic mesh we use?
Well, thank you for the nice comments, but I don't know if it's. I mean, this is a result of the finite element modeling. It allows us to use this dynamic mesh, and I don't know if you use the same, but we are really just solving the elastic equation for the fluid. So it's just it's no other. There are no dynamic things to the mesh other than the boundary conditions of the motions of the structure. We just pass it to the solvent.
So you didn't do any special treatment for the dynamic mesh?
No. The only thing we do is to inside the element loop, when we compute the Jacobin, we just use that to scale the elastic modulus. So to avoid wrapping. So that is. It's a very user-friendly method, I would say.
Yeah. Thank you. And I may miss the beginning part of your presentation, so I would like to know whether you did any modification to the LES model or the boundary conditions, because I was always almost the last part of the CFD. Yeah.
Okay, so we don't do any special treatment of the boundary conditions other than using this penalty formulation for the no slip, the weakly enforced ones. But otherwise we use like strongly prescribing the velocity. It's also for the turbulence. So it's just standard boundary conditions, really.
Okay. Then have you considered about to try the DES simulation? Maybe you can save much more time and get a better boundary around the bridge deck.
I think the VMS turbulence model kind of represents a DES in a sense, because it is consistent in both the laminar and the turbulent regimes. So you doesn't have to consider this decomposition, this mixture of RANS and LES, because it's the functionality is there. So it's Since it is, in that sense, it is really a DS method, perhaps.
Okay. And it's really also very interesting to see your future work about the wave surface simulations. It's really interesting. But any special reasons that you choose the level set method? Because I think it will cause a little mass conservation problem according to our experience. Especially if you calculate the force on the bridge deck on the other structures. So any special reasons? Or you can also try the WAVE method if you want.
Well, this was just I haven't really done that, so it's I have no experience with that. Perhaps it was just as an example. So I guess there might exist many other as good methods, but for the level set, I mean, it has been used for a number of successful implementations, and you can, if you do the mass correction step afterwards, you have mass balance to the computer precision. So
maybe different software have a different way to realize the method, but according to our experience, if you use level set method for the very severe wave conditions, it may cause problem to catch the false details. Another suggestion is maybe you can combine with the relaxation method, which can give you a better maybe comparison with the analytical wave elevations. But just as a suggestion, it's really nice to see your results. Very interesting. Thank you.
Yeah, thank you for the comments. I have taken the notes, so
thank you very much.
Look into, so yeah. So I guess there is several approaches to this problem.
Maybe you have a chance to discuss later.
Perhaps. So, as I said, this was just something I did the last couple of days. So it's an interesting problem. And you get some nice coupled problems to challenge.
Thank you. That's my question. Thank you so much.
Thanks.
Hi, can I ask 2 small questions, Kjersti?
Yes, go ahead.
Yes, so Tore, thanks a lot for your nice presentation. 2 small questions. The first one is, I see you compare the Hardanger bridge aerodynamic coefficients between CFD and experiment. In that case, is the space ratio the same? The length divided by the width of the deck, are they exactly the same, or?
No, we have simulated a bit, just a strip of the wind tunnel, so it's like 1 meter or between half a meter and a meter in width, and the width in the wind tunnel is 2.7. So we are simulating a bit narrower, but sufficiently wide to capture the 3-dimensional turbulent structures. So yeah, that's just to save computational time, you know.
Yeah. Okay. And the second question would be, because I think in the very beginning of your slide you mentioned the Reynolds number importance. That's one of the goal for you to do simulation, right? Because in the wind tunnel you cannot achieve the real scale Reynolds number. So in your simulations, when you validate your results with the experiment, are they in the same Reynolds number? Or?
Yeah, so that was our motivation to do it in the model scale, so we can do the same wind velocities and try to recreate it as close as possible. So we have our simulation is for the same data as in wind tunnel.
Yeah, but then after that, have you done the real case scenario with the real Reynolds number? Because that's probably the goal for you to do a CFD, maybe, right?
Yeah.
Done that, or do you have any comments on that?
I totally agree, and that is on our bucket list, but we haven't done that yet. The reason we haven't, I guess, it's mostly because we were trying to prove the community of the accuracy of these methods, and then we had to compare with some one-to-one experiments, but it would be a very interesting thing to just reduce the viscosity and then see what happens when you increase the Reynolds number. So it's of course it's.
Yeah, because I think probably when you increase the Reynolds number, you will jump to a different fluid regime, and that probably could, probably you need other numerical schemes for simulation, right? So that could also be really challenging in numerical simulations.
Yeah, I agree. But I think the assumption of the wind tunnel experiments is that you have come to sufficiently high Reynolds numbers, so you don't so you don't longer have the same dependency. But of course, it will probably happen some interesting stuff. But I think also that is where the weakly enforced boundary conditions come into its power, because if the boundary layers become even thinner, you can still have a sort of relax the increasing need for the meshing. So it's, but of course we haven't done it, so we don't know what will happen.
But according to your study, is there any available literature that covers the high Reynolds number case, or more close to the real kind of Reynolds number case for bridge deck simulation in terms of CFD?
I think for the same method that we have used, it has been used a lot for wind turbine applications. So I think if you go to if you search VMS and wind turbines and see the recent publications, I think that is sort of the same model as we are using. So that is, but yeah, I think that's the best literature to see our methods.
Okay, thanks a lot for your presentation.
Thank you.
Okay, and thank you, Tore. And I think with this we will stop the 2018 presentation from the Coastal Highway project. I would just like to remind everyone that on January 4th we will have Thomas Wuff talking about modeling and analysis of damping in extreme bridges. So you're all most welcome to come back on January 4th. And with that, I wish you a great holiday. Thank you.